My name is Arlie Nutzel, Application Engineer in the Mechanical Analysis Division of Mentor Graphics. Today, I will be presenting the last in a multi-part series of webinars addressing aerospace fuel system modeling. I'm going to start today's presentation with a brief overview of the benefits of using both one-dimensional and three-dimensional CFD software in the engineering process. We will then look at a review of the one-dimensional fuel system model for a typical two-engine passenger aircraft we used in the last 3 sessions. After the overview, we'll look at adding a pair of jet or ejector pumps to the tank system. We'll use three-dimensional CFD to generate performance data for our pump, and then use them in a 1D simulation. After the case study, we'll end with a question and answer session. Risk is always a concern for companies, and usually as a project progresses, the risks associated with the project tend to decrease. One of the main driving factors behind this is the increase in information that naturally happens as a project matures. By gaining knowledge very early in the process, designers and engineers can lower that risk even sooner. This is where upfront simulation can add significant value to the process, by allowing engineers and designers to investigate a growing number of prototypes virtually before any physical models are constructed. Investment in upfront CFD can have a significant value by lowering physical testing efforts later in the design. Because physical testing is time-consuming and expensive, virtual prototyping allows more variants to be examined in a shorter amount of time. Flowmaster fits into this idea because it's a one-dimensional computational fluid dynamics simulation tool that allows engineers to simulate complex thermofluid problems at a system level so that they can understand aspects of the design such as pressure, temperature, and flow rate throughout the design. Access to performance data early in the design process is always a challenge, but Flowmaster supplies built-in data from DS Miller out of the box to give you a baseline to work from. You can investigate both steady-state and transient behavior in your system, and you have the ability to simulate different types of fluids, including liquids, gases, refrigerants, and steam. There are also a host of specialty solvers for both complex phenomenon like swirl and priming, or for making potentially repetitive tasks simple, such as performing a flow balancing analysis. Like Flowmaster, FloEFD is also a powerful tool for upfront simulation. Because FloEFD is a fully featured 3D solution that runs on native CAD, it can apply to early concept designs that continue to evolve over time to a final product. Because FloEFD uses a highly automated and efficient mesher, users can save significant amounts of time over physical testing and other traditional CFD tools. Its simple user interface, proprietary wall functions, and automatic flow regime detection put the benefits of 3D CFD analysis in the hands of engineers who may not have had the training to drive more traditional manual CFD tools. Lastly, FloEFD can leverage the parametric capabilities of the underlying CAD tool and perform automated what-if studies, just like Flowmaster. You can even export data directly to Flowmaster, which is a topic we'll cover today. Mentor Graphics has been helping its users meet these requirements for over 25 years across many industries throughout the world, including our focus today, the aerospace industry. Before we look at today's studies, let's take a few minutes to review what we did last time and expand on the basic model with the addition of a jet pump assembly to the wing tanks. Here's the schematic representation of the simplified passenger aircraft fuel system that we built and used in the previous presentations. The 3 large blue sections represent the wing and the center fuel tanks. The white boxes represent pumps, and the fuel feed and transfer plumbing is represented in green. And refueling lines are represented in dark blue. Shutoff valves are depicted throughout the model as the circular symbols indicating normally open or normally closed. Here's a Flowmaster system model drawn directly on top of the schematic image. It includes source components for our boundary conditions, and extra loss components for items like filters and couplings. Again, the tanks do not take up the whole area outlined in light blue, but are instead single discrete components. The thin link lines represent a direct connection between adjacent components, but they're not pipes themselves. Nodes sit in the middle of the links and serve as convenient points to enter elevation data and interrogate flow results of temperature and total pressure. We took a more detailed look at this arrangement of pipes, pumps, valves, and tanks in the first 2 presentations. For a more thorough explanation of the base model, you can rewatch those earlier presentations. For today's study, we're going to focus specifically on the wing tank system in detail. In our model, we're drawing fuel from our tanks with mechanical fuel pumps. This works quite well, but as the model is refined and we take other design considerations into account, we might run into some limitations on where the pumps can be placed. Furthermore, most mechanical pumps must be fully wetted to function properly. This means that sometimes there's unusable fuel left in the bottom of the tank. One solution is to add jet pumps that can be placed in the lowest portion of the tank. These pumps have no moving parts and can scavenge the last remaining amount of fuel. A constant issue for any aircraft is water condensation within the tank. Any water in the fuel will tend to settle to the bottom of the tank because of density differences. An additional benefit to our added jet pump is that any small amount of water that accumulates can be removed before a large buildup could cause harm. Here's our existing model from the last session. And here is our updated model with the addition of a jet pump and collector cell to each set of wing tanks. Let's take a closer look at the left-hand wing tank. The inner wing tank is now connected to a smaller collector cell. Instead of drawing from the inner tank, the mechanical fuel pumps now pull fuel directly from this cell. There is a gravity feed connection between the inner tank and the collector cell, but due to structural constraints, this connection does not extend to the very bottom of the inner tank. Left unaided, this amount of fuel would go unused. To extract the fuel from the inner wing tank once it gets too low to gravity feed, we've added a jet pump with the suction side connected to the lowest sump point on the inner wing tank. The pump feeds the collector cell by using the motive energy provided by a small amount of high-pressure fuel bled directly from the mechanical fuel pumps. Now that our model is built, let's look at how to use the jet pump component. In contrast to most other components in Flowmaster, the jet pump does not come pre-supplied with performance data. Instead, you have two options to define performance. The first method is to enter detailed geometry for the pump, and Flowmaster can apply a built-in empirical correlation for jet pump behavior. The second option is a more rigorous data-based approach. The pump requires a curve of flow ratio versus head ratio, and a curve of motive flow rate versus pressure difference between the motive and suction arms. These data can come from many sources, including the vendor of the pump, physical testing, or what we'll demonstrate today, 3D computational fluid dynamics. Let's switch gears and look at using FloEFD, a CAD-embedded concurrent CFD tool, and how we can leverage its power to generate 1D data for use in Flowmaster. FloEFD has several key technologies that make it a very good fit for 1D data generation for Flowmaster. FloEFD is CAD-embedded. It runs inside of several CAD packages, including CATIA V5, Pro Engineer, NX, and a standalone tool using the SolidWorks engine. Today, we'll work with the CATIA version because CATIA is so prevalent throughout the aerospace industry. FloEFD has what we call an engineering user interface. We've designed it to work how engineers expect to work, allowing you to change units, fluid properties, physics, and simulation conditions quickly and easily in a wizard-based approach. With CFD, the devil is in the details. Because we designed this tool for engineers as well as seasoned CFD analysts, we apply automated modified wall functions to properly capture boundary layer effects regardless of the density of the mesh in the boundary layer. We've also automated the solver to automatically determine the flow regime between laminar, turbulent, or transitional. But most importantly, we've highly automated the mesher. The mesher is geometry aware. If the CAD changes, the mesh changes automatically. It's optionally solution adaptive, updating as your problem solves, putting more mesh where it's needed intelligently. You also, of course, have the full ability to modify and drive the mesh density where you want it to go. Because FloEFD is completely CAD embedded, we can run parametric studies not only varying flow conditions, but also the actual geometry over the course of a study. The parametric tool has a built-in Flowmaster export utility that makes getting data back to Flowmaster as seamless as possible. The Flowmaster 3D import tool supports a wide range of geometry. For two-armed components with one inlet and outlet, Flowmaster uses a discrete loss model that uses a loss coefficient versus Reynolds number curve. If temperature change is included in the data, a thermal bridge model is assumed, which adds a curve of heat transfer effectiveness versus Reynolds number and a contact area calculated from the solid geometry. If a three-armed component is imported, Flowmaster assumes either a T-junction or a jet pump depending on behavior to capture Venturi-type effects. The heat exchanger, with its two separate internal fluid circuits, is the only four-arm geometry currently supported. Loss curves for each of the two flow paths are imported, along with heat transfer information in the form of an effectiveness map. We're working hard to support more types of geometry in the near future. With the FloEFD background information out of the way, let's take a look at how to set up a simulation starting from raw CAD and ending with a Flowmaster component. In CATIA, FloEFD shows up as its own workbench and adds some elements to the project tree. In other CAD tools, FloEFD appears as a tab inside the project tree. In the model tree, besides the familiar geometry elements, are elements for the project settings, input data like boundary conditions, simulation goals, and mesh settings, and results, which contain elements for creating and saving in CAD plots, studies, and reports. To start a new project from bare CAD, you simply run the project wizard from the FloEFD menu. This project wizard is a prime example of FloEFD's engineering user interface. In a step-by-step fashion, we choose units, the physics to consider in the simulation, including heat transfer, gravity effects, and rotation, the fluids to use in our simulation, and lastly, the initial conditions like temperature, pressure, and initial velocity. Once the wizard is complete, we can prepare our geometry for simulation. For an internal flow problem, like we'll perform on this jet pump, we need to fully seal any openings. FloEFD has an automated tool that can generate what we call lids on any hole or gap that we find. Once the geometry is sealed, FloEFD performs a check and builds a solid model of the internal fluid cavity. We can optionally display or export this geometry if we want, but it usually stays behind the scenes. FloEFD then calculates a computational domain surrounding the relevant fluid geometry. We could resize this if we want, or even slice the volume in half and do an axisymmetric simulation to save computational resources. We then must manually apply the boundary conditions that we want to any face in the model. Although typically you'd choose your lids as the boundary conditions, you're not required to. Simply click a face and add a new boundary. You can combine multiple faces, switch between flow, pressure, and wall boundary types, and even add swirl or a non-uniform velocity profile by transferring results from a different study. The mesh, although highly automated, can be manually driven to add grid cells where they're needed. The first step is with a simple slider bar that spans from 1 to 7. This controls the number of refinement steps the mesh will take as needed, with each step creating 8 grid cells in place of its lower level parent cell. At higher levels, advanced features like solution adaptive refinement are automatically invoked. You can specify minimum gaps that you want properly resolved, and you can automatically ignore thin gaps, something very commonly found in large CAD assemblies. You can manually refine the mesh where you want by selecting specific geometry, adding optional control planes, or even disabled bodies into the CAD model to serve as mesh structure. The last step you should take before running a simulation is to create goals. Goals are predefined, customized measurements. Although completely optional, goals are a highly useful tool for simplifying your results down to key performance parameters like total flow rate and pressure drop. Goals can be combined via complex equations and can be used for convergence monitoring in the solver. The goals required for the Flowmaster export capability we'll look at shortly are created automatically and do not need to be manually created. Once the model is prepped, boundary conditions are set, and goals are made, you can run a simulation via the run command. Running the simulation launches the solver. The solver is the only aspect of FloEFD that does not happen directly in CAD. Instead, a second window is launched to monitor the progress of the solve. Here you can create custom-defined preview plots for parameters like pressure, velocity, and even the mesh. You can also plot your goals to have a real-time monitor on their current value and their trend towards convergence. The solver can run locally or on a remote Windows or Linux machine. Parametric studies can be performed on multiple machines at once to improve performance. Once the solve is complete, the results are loaded back into the CAD interface. Here you can draw results directly on the native CAD. The first example of a result is a cut plot. This one shows contours of velocity with overlaid streamlines. The cut plane can be manually adjusted with a live preview. We can also generate three-dimensional flow trajectories inside of the fluid region. Lastly, tabular results like goals can be drawn or exported to other tools like Microsoft Excel. For Flowmaster part characterization, we need to run multiple simulations to generate data over a wide range of flow conditions. To do that, we can use the parametric study tool built into FloEFD. This tool leverages the parametric capabilities of the 3D CAD package we integrate with to allow you to vary boundary conditions, dimensions, or constraints in your model. To use it, you simply set up an experiment manually or with an automated range of values. Select the goals you want to solve for, though everything that Flowmaster needs to build a component will automatically be extracted. Once the study is complete, you can view your goals right on the plot, and you can simply choose the Flowmaster curve export option and save it to a file for use in Flowmaster. That file is simply a raw record of the flow conditions at each boundary at each experimental point. Each point contains data for flow, pressure, temperature, density, viscosity, enthalpy, and heat capacity. This way, non-dimensional curves can be created so that Flowmaster can extrapolate performance of your part over a wide range of fluids, temperatures, and pressures. I'm now going to switch to FloEFD and show you a quick example of what we've looked at so far. So I'd like to show you how this works in CATIA V5. Right now we're looking at a raw CAD assembly. I've got a split plane enabled, but we're looking at FloEFD with the lids already applied. And you can see each lid is an automatically generated part that just gets added to the model. You can see I have a hidden part of the complete geometry. And that's what's actually going to be used. This one is visible but disabled, so FloEFD does not see it. What I've done is I've gone through, and after running the wizard that we saw in the presentation, I can apply boundary conditions to each lid that I want. In this case, I have a motive flow boundary condition, a discharge pressure boundary condition, and a suction pressure boundary condition. Any one of these I can double click on and modify as I see fit. I could change it to a pressure boundary condition, or I could simply change its value. Let's do volumetric flow rate and make this 15. With my boundary conditions set, I can review my goals that I've created. I can make a new one or look at what I have. And again, these are just created by clicking existing faces or surfaces in the model and selecting what I want to measure. In this case, pressures, flow rates, or in this case, I've calculated a pressure ratio based on some differences between various pressures. With the goals complete, I can define my mesh, and I can go in here to the initial mesh settings, and here we can visualize what the basic mesh looks like and what each refinement level looks like. And these refinement levels will be placed automatically depending on what FloEFD sees as being relevant for the model. Here's our setting for minimum gap, so we can set a minimum gap for this channel to make sure it's properly captured. And we can also ignore things like thin gaps in our model that might otherwise be counted as leaks. I'm setting a relatively low mesh level because I'm going to run this live and I want it to complete in a reasonable amount of time, but for real analysis we'd want to crank the result resolution up a little bit to get better, more high quality results. So with that done, I can run a simulation right from this play button, or I could go to FloEFD, solve, and run. And it's going to prompt to make a new mesh and to solve, and I can run this on my computer, on a remote machine, use as many cores as I want. So I'll click run. And that will prompt the solver window to open. You can see it's preparing the model, it's meshing. Meshing actually happens very, very quickly. You can see we've just meshed. And this is, again, with a coarse mesh setting, only 24,000 cells. Normally you'd see maybe upwards of an order of magnitude higher in a really high quality mesh, but I want this to run nice and fast. And you can see that we're running. We can see the solution coming into shape, and we can see our goals being plotted on a normalized scale. We can watch them trend towards convergence here, and they're coming together nicely. This should take, around 110 iterations or so. You can see some of our goals are already converged, some of our boundary conditions where we've defined these things. They're the first to converge, but some of our additional goals come a little bit later, and that's why they're so important. These goals can be used to determine convergence. So give this another few seconds to finish up, and now FloEFD is done, and we can close the solver window. With the solve complete, we can expand this results portion and show a predefined cut plot that we'd like, and it's basing these off of the latest results. We can go in here and change from contours of velocity to contours of pressure and see what that looks like. And we could even change the scale, so we can auto scale that if we want. We can even move it out of the current plane to any plane we want. So that's kind of a nice thing to be able to do. You can also turn off the mesh, turn off these GUI drawn stream or GPU drawn streamlines if we want. The cut plot done, I can also add some flow trajectories. Again, the way these work is we select faces where we want the flow trajectories to come from, and it will draw them. So here I've selected this inlet and this inlet independently, and they come together to make our flow trajectories. You can see each of those faces is selected as a source for flow trajectories. So now what we want to do is run a parametric study. So I'll open our latest parametric study that's already saved. You can see all we did was vary the volume flow rate of the mode of flow. You can see in several steps. But if we wanted, we could add another parameter of a boundary condition, maybe the discharge pressure, and we could add that to our study. You could click on this, maybe vary it between 14 and 30 psi in 3 steps. And what that will do is it will automatically generate a scenario for us that goes all the way out, and it knows it needs to recalculate all of these studies. Once those are done, we can export the Flowmaster curve and see what we looked at, just like we did in the presentation. Now that you've seen how to generate Flowmaster data, let's put it to use. Once the Flowmaster curve is created, we can import it into Flowmaster either as an individual data curve or as a complete component. To do this, simply click on the component catalog and create a new FloEFD component. Flowmaster will parse the data and automatically determine what type of component you want to make. The component creation tool will preview the parsed and calculated performance data. Here we can see the first curve a jet pump needs, flow ratio versus head ratio. And here on the next tab is the other mandatory curve, motive flow rate versus pressure difference. Once we're done with this step, Flowmaster adds the component to the catalog and automatically populates it with the data we just generated. It's always a good idea to test a new component out in isolation before it's used in a larger network. Unlike most components, FloEFD sourced components require no further data to use. Relevant data like the curves are pre-applied. All you have to do is add boundary conditions and run an analysis, and the component should perform exactly as FloEFD predicted during the characterization step. Lastly, the component maintains a link to the FloEFD generated data for reference or manual post-processing. After the unit test, we can put the jet pump into our model and run a series of analyses. Let's look at the results of 2 transient simulations. In the first simulation, we've included the jet pump but blocked the mode of flow, so the tanks will only feed into the collector cell via gravity. The connection between each section of the tanks is via a series of holes in the ribs that separate each compartment. These holes span almost the entire height of the tank, but the bottom 2 inches of the tank is blocked by structure. As shown with the blue line, you can see the outer tank draining briefly into the inner tank marked in red. The outer tank stops flowing as the level of fuel drops below the holes in the rib at approximately 2 inches, rendering the remaining 2 inches of fuel in that tank unusable. The inner tank in red and the collector cell in green both drain together. The collector cell is drained via the mechanical fuel pumps, and the inner tank drains via gravity into the collector cell until it too reaches about 2 inches of height and can no longer drain. The tank is exhausted of all usable fuel in about 125 seconds. Now let's look at a case with the jet pump enabled. Here, the jet pump is moving fuel from the inner tank to the collector cell at a rate of around 10 gallons per minute. In this case, the inner tank drains much faster, but the fuel is being transferred to the collector cell to feed the pumps. Because the suction inlet to the jet pump can be placed at the lowest point in the tank, we can drain almost all of the fuel out of it before it stops providing flow. At this point, the fuel level in the collector cell starts to drop quickly until it too is completely exhausted. In this case, because more fuel is available to use, the tank does not drain for 320 seconds, a significant improvement. Today we looked at the problem of unusable fuel and how adding specialty pumps like jet pumps to the design can help with fuel scavenging. As we learned, the jet pump has unique performance data requirements that make them a good candidate for characterization via CFD. To do that, we first looked at FloEFD, a fast and easy-to-use CAD-embedded 3D CFD tool. We then performed a parametric study on a sample jet pump, automatically exported the data to Flowmaster, and then included it in a 1D analysis. As this is the last presentation in the series, let's take a quick look at where we've come. We've started with a basic 1D system model of an aircraft fuel system, and then we put it to use studying ground refueling, using Flowmaster to size components and balance flow. In the second presentation, we added active controls to assist in balancing flow during the refueling operation. We also applied controls to in-flight transfer of fuel from tank to tank. In the third presentation, we turned our attention to adding fidelity and detail to the tank model by adding advanced tanks and a venting system. We used the capabilities of the advanced tanks to study fuel tank inerting. And lastly, we looked at adding jet pumps along with 3D part characterization using FloEFD.